We now look at a first application of QED to the case of scattering between electrons. We will describe this process in the center of mass of the two electrons, therefore their momenta are always opposite and equal in magnitude. At lowest order in perturbation theory, we have two Feynman diagrams which contribute to this amplitude. The first diagram is the direct term, and the second diagram is the exchange term because the electrons are indistinguishable. So let's apply the Feynman rules to calculate the amplitude for the first diagram, the direct term. The fact that we represent one vertex before the other is just for convenience. In fact, we have different time orderings. We could move this vertex before if we want, but that's the same thing. The technique to write the amplitude is to read the diagram from right to left, so backward in time. We also need to label each line by its form momentum and for the fermionic line by their spin. For the photon, applying energy momentum conservation at this vertex, we see that its momentum must be p minus k. So 1 corresponds to an outgoing fermion, therefore its spinor is u bar. Then in 2 we have a vertex. In principle, I should also have an energy momentum conservation written explicitly at this vertex. However, because we already have used energy momentum conservation at this one to write the propagator for the photon as p minus k, and we know we have an overall energy momentum conservation between p dash and k dash. Therefore, there is no need for this additional energy momentum for this vertex because it's going to be redundant and it's going to be removed by rule number 7. So in 3 we have a u spinor. Then in 4 we have the propagator for the photon. In principle, we should integrate over the momentum for the internal line, the photon. However, because of energy conservation at each vertex, there is only one possible value which survives and which is killed by the delta function. So we have already used that in writing the momentum for the photon as p minus k. Then in 5 we have a u bar. In 6 we have the vertex. And in 7 we have u for the momentum p and spin s. We introduced earlier a property for the spinors. We see that using this property we can recognize it here and therefore cancel the term with the division by m squared. So note that these two terms in between brackets are just C numbers. So far we haven't used the fact that we were in the center of mass frame, and we can use that in order to change our p minus k squared into Euclidean vectors. The exchange term can be calculated in the same way. And now in order to get a cross-section, which is proportional to the probability for this process, we need to calculate the modulus squared of the amplitude.